Hey there, this is Sriram Jayaraman, a student pursuing Masters in Cybersecurity at the University of Waikato. This is the first in a series of 3 presenting the reading of papers published in distinguished venues in the recent past. These papers offer great insight onto the latest findings in the field of self-adaptive systems. Getting on to the first paper, this paper is titled Constructivist Approach to State-Space Adaptation in Reinforcement Learning. We will get to the specifics later. This was presented at the IEEE Conference on Self-Adaptive and Self-Organizing Systems, SASO, which was co-located with the International Conference on Autonomic Computing, ICAC, at Umeå, Sweden, which happened at around June 2019. With regards to the problem discussed by the paper, we all know how the IoT space has been exploded in the recent past. IoT was conceptualized with the motive to get all things connected to make life simpler. The diverse range of applications that IoT brings forth makes it pervasive and ubiquitous, all the more making it highly dynamic. In this dynamic environment, with sensors that change state very frequently, it requires a lot of time and effort to selectively choose states manually for self-adaptation and learning. This paper tries to solve the problem of manual state space selection with respect to dynamic sensor-based environment in the IoT space. While attempts have been made to address this concern, they all have some manual process. For example, manual inputs for state space selection or specification, or some techniques do not even address non-stationary inputs. Manual intervention requires a lot of expertise in the domain and has been proved to be very costly. Before moving on into much detail, we would need to understand 2 key terms: constructivism and reinforcement learning. Constructivism is the approach that is designed behind the theory that human knowledge base is learned through assimilation, newer addition to the existing framework, or accommodation, manipulation of already known information. Reinforcement learning is an area of machine learning concerned with how software agents ought to take actions in an environment in order to maximize the notion of cumulative reward. This is an unsupervised learning technique. Previous studies have found that constructivism works for roadside traffic control. Combining constructivism and RL in a conceptual way can benefit from the advantages of both approaches. Simple state space refinement can be done at runtime through grid-based discretization. State aggregation techniques have been known to reduce state space, improving performance, but the initial discretization is manual and requires domain knowledge. Growing neural gas, GNG in short, has been used for state space partitioning techniques which underlie Q-learning. Moving on, the authors propose that with the use of constructivism reinforcement learning, using multi-layer growing neural gas, MLGNG in short, to optimize learning and a runtime selection engine to maintain long-term performance, self-adaptation can be achieved to a certain extent. Given a sensor-based state space SRK, it is possible to generate a learned state space SLK to improve the learning process. Storing both these states benefit one another as the quality of suggested action by either updates the learning processes of both. The study aims to achieve the goal in 2 parts: coarser-grained state space generation and the runtime selection of state spaces based on the repository of state spaces that have been stored historically. While RL has been used with GNG before, MLGNG is a state-of-the-art technique to perform autonomous computing, with autonomous state selection going one level deeper to not only learning to adapt with the process but also to learn to adapt with the environment itself. This is a complete autonomous process, the likes of which has never been implemented in the past. Moving on, the goals of the evaluation were twofold. Provide optimized state spaces with good sensor level granularity with MLGNG. In the presence of changing state space representations, the selector should adapt to use more suitable state spaces, maintaining a stable performance. The implementation was validated through two studies. One, a mountain car scenario, and two, a ride-sharing scenario. Mountain car scenario. This is used to evaluate the number of episodes required to reach stable performance and the ability of the selector to maintain stable performance without external factors affecting it. It is a classical benchmark in RL. The scenario is that the agent needs to adapt to drive a car up a steep hill. The engine cannot do this, and the agent needs to learn to reverse up to the opposite hill to gain potential energy to complete the task. GNGQ, grid representation, is faster to show good performance but fluctuates until later. MLGNG is slow to converge, as can be seen from the figure here, but when it fully converges, it does so before GNGQ's fluctuations stabilize, and it manages to sustain a good performance. In the car and ride-sharing scenario, performance with external factors and a dynamically changing environment in a large-scale scenario is evaluated. This real-world scenario deals with autonomous cars for decentralized ride-sharing. Each car has one RL agent to it, and its goal is to minimize waiting times while increasing requests served and occupancy. If the car is idle, it will wait around in the same location or move to another location where incoming requests are high. The results. With 5 days of simulation worth, grid serves only 53% of requests with an average wait time of 3 minutes, while MLGNG has an average wait time of 2.807 minutes with 74% of requests served, which is a whooping amount as compared to the grid-based ones. With growing days, grid explores all state spaces and the differences are not clear-cut. This indicates that the proposed MLGNG performs faster, but in the long run is on par with the existing methodologies. The pros of the paper include that it does so well with its evaluation process to measure how a real-world scenario would be like instead of just running hypothetical scenarios. This can be a proof to serve concrete applications of the constructivist approach. With future work, if it can be learned to optimize the learned state spaces to converge faster, it would really be beneficial, as longer runs have the same performance as the grid-based ones. So faster conversion rates would make it a viable and strong method for speedy and sustained performance. That is all I have for this paper for now. Any feedback on this is much appreciated. Thanks for listening. Cheers.